concentrics at maybe about 8 to 15 or so this morning. What do you trying to get?
Yeah, I do on that, but
What is the other side?
a lot of those cars.
How many of them go here?
A lot. That's just super common now. I see them all the time. You don't notice them until you own one. Then you see them, yeah, then you see them literally like 25 days.
When I got my Civ, it's like, a lot of people work, a lot of people, I remember seeing a car in like a TV show on every day. The next week I was
Okay, let's get started. So today I'm just gonna go ahead and do the requested problems, and then there will be a time in the middle of the class where I'll put you to work on some new type of problems that we're on the stuff we're learning today, and then those we can do some on the board. Okay, does that sound okay? All right. So this one's asking about this parallelogram: P1, P2, P3, P4. And it wants us to verify that the opposite sides are indeed parallel, because so parallelogram that's what's defined as opposite sides parallel, right? And then find the area. So let's just quickly sketch these points so we can know for sure, we need to know for sure where the opposite corners lie, right? Does that make sense? So that we're finding the right vectors to start with. So I got 0, 0, 0. 2, 4, 2, 3, 0, 0, and then 5, 4, 2. Okay, so it's pretty clear that what this looks like. These are up as equals 2. So these are all as equals 2. These are as equals 0. So this was P1. This was P2. Yeah, so look, it didn't go around. P1, P2, P3, P4 does not go around a loop. Do you see that? So that was good that we did this first, because it goes P1, P2, and then P3 is across the kitty corner to P2, and then P4 is this last one. So you might be tempted to say, oh, P1, P2 should be the same as P3, P4, right? But it's not. It's going to be P1, P3. Should be the same vector as what? P2, P4. So we're going to verify that. And what else are we going to verify? That P1, P2 is the same as P3, P4. So how would we verify those? How do you find a vector from one point to another? Final minus initial, right? So we're going to do final minus initial. So just quickly here, P3, P1 would be, P1, P3 would be the vector 3, 0, 0, right? And P2, P4, 3, 0, 0. Okay, so both of these are 3, 0, 0. Check. And then for these two, P1, P2 would be 2, 4, 2, right? 2, 4, 2. So for these two now, are they both 2, 4, 2? P3, P4 would be 2, 4, 2. So I think these both check out. That opposite sides are the same vector. Opposite sides of the parallelogram are the exact same vector. Are we good? Okay, cool. So now they want you to find the area of the parallelogram. So what did we find last time? That the area of the parallelogram? Magnitude of the cross product, right? So I can do, let's make it as easy as I can on myself. So P1, P3 is a nice easy vector, right? That's what? That's the 3, 0, 0 vector. And let's do P1, P3 cross P1, P2, which would be 2, 4, 2. So the area is going to be the magnitude of P1, P3 cross P1, P2. So that's how we're gonna. So using the cross product, then it allows us to not have to figure out what this slanted height in space is, right? So like we could do base times height, but finding that height would be a little hard because we'd have to find the angle of this slanted parallelogram in space. Difficult, right? So that's where the cross product comes in. We don't have to deal with any angles, right? Because we know that magnitude of that cross product is already, magnitude of A, magnitude of B sine theta. So we can do it this way and avoid figuring out what the angle is, right?
Can't we just do like length width? If we know the magnitudes of both sides?
That's not the area of a parallelogram, though. That's a rectangle. Area of a parallelogram is base times height, right? So you have to find this height right here. It's base times height, not side. A rectangle would be length times width, but a parallelogram, it's base times height. Does that make sense? Okay. So cross product then, be ijk. What do we say? 300 cross 242. I'm going to do my determinant of that matrix, and so I showed you to write the first two rows again, right? First two columns again. And then we're going to go down 3 diagonals this way and add, and then multiply down 3 diagonals this way and subtract, right? So that's going to be 0i, 0j, 12k, minus 0k, 0i, minus 6j. Vector is, thank you, 0, negative 612. Magnitude will be the area of that parallelogram. So it's going to be square root of 36 plus 144, 180. Is that right?
Yeah.
So magnitude then is square root 180, which is, got a 9 in there and a 4 in there, so 3, 6, this is extra credit. 6 times radical 5. 36 times 5, 180?
Yep.
Okay, 6 radical 5. Questions?
I got a question.
Please.
So under the radical P1, P3 times P1, P2,
Uh-huh.
you have the radical of A, the radical of B, sine theta.
Magnitude.
The magnitude.
Right,
Magnitude
okay.
of A, magnitude of B, sine theta.
Yeah.
Where did the sine theta, did you not use that equation at all?
I did not use that. These are equivalent. Well, I was
those are
showing you that this would be like, before you ever learn anything about vectors, this would be how you would have to get the area of the parallelogram.
Okay.
What makes this hard? It's slanted in space. So how are we going to get the height of this parallelogram slanted in space? How are we going to get the sine theta of a vector slanted in space?
Yeah.
Difficult.
So they're
So-
equivalent. Okay.
So they're equivalent. So this makes it a lot easier to find the cross product, take the magnitude. And we showed this was true in class last time. Right? Because this is theta here.
Forgot, I think.
Yeah, that's okay. So this is A, right? So it's magnitude of A sine theta is the height,
Oh, okay.
times the magnitude of B is the base.
Yeah, that makes sense.
So that goes back to the formula for the,
Oh, because you just put the sign on the outside. Yeah, I remember that. Okay.
remember?
Yeah. I
Yeah, so the sine theta would be with the
With the
A,
but
and then there'd be the base.
Okay.
Yeah.
Yeah, that makes sense.
Same as the magnitude of the cross product, much easier, right? Because we don't have to deal with any angles of, vectors angled in space.
And for on the test, if you leave it as radical 180, is that correct?
Yes, I really care very little about this.
Okay.
I want you to understand stuff.
I do have a question though. The cross product that becomes a vector and then you find the magnitude of it.
Yeah.
My vector was different. It was 0, 6, negative 12.
Right, so if you chose different directions, like if you did,
It's just the difference in direction.
you probably didn't do them tail to tail. So you probably didn't pick vectors that were tail to tail. You probably picked vectors that were tip to tail.
Right.
So for instance, you did P1, P3 cross P2, P1,
Okay.
and that will give you the opposite.
Okay.
But when it comes to the magnitude, that doesn't matter. But for the cross product, it's the opposite vector, right? It'll point the other way.
Okay.
So that matters if you want the cross product vector. But if you want the magnitude, it doesn't matter.
So the cross product vector, is it tail to tail or tip to tail?
Right-hand rule. So it's
Okay.
by the right-hand rule. First vector, index finger. Second vector, third finger. Then your thumb gives you the direction. So if you flip one of those, then it's going to flip the right-hand rule, and you're going to get the other vector.
Okay.
Yes, sir, David.
So I'm still having trouble figuring out where you found the height. So P1, P2, and P1, P3, the vectors just be cross right so you find the area.
Yep.
For that. And so where did you find the height?
I never found the height. We showed in class last time that so this is the formula for the area of a parallelogram, like from geometry, right? So the area of the base times the height. But then when we kind of developed the whole cross product, we noted when we got to this formula, we said, oh, that's just the magnitude of the cross product. Well, when you do the cross product and take the magnitude, you never have to find the height or the angle. But since they're equal, you can do it that way. It's kind of like there's two ways to find the dot product, right? You can do product of the components and add, or you can do magnitude of the first times magnitude of the second times cosine theta. They both give you the same number. So if you do the product of the components, the products of the components and add, you never have to deal with the angle. Is this helping? So this is two things. It's the formula for the area of a parallelogram, but it's also the formula for the magnitude of the cross product. So they're equal. Therefore, the magnitude of the cross product equals the area of a parallelogram, and we can find the area of the parallelogram that way. Is it better? You're nodding now, so I think we got it. Cool. Other questions? All right. Can we go next problem? It's 55. Okay, so they want an area vector. So we talked about area vectors. They're the magnitude that has the same as the area, and then the direction is orthogonal, right? So this is circle of radius 2 in the YZ plane facing the direction of, okay. So they didn't really tell you where this circle was. They just said a YZ plane, right? But it wouldn't matter. So I'll just make it like this. If you made it center at the origin, that's fine, doesn't matter. But its radius is 2. So if, from last time, an area vector, its direction is orthogonal to the region, and the magnitude of the vector is the magnitude of the area. Yes, sir?
So wouldn't this one just be the radius would be 2 pi r projected to be
That's circumference. What's the area?
pi r squared?
Pi r squared. So our area is 4 pi.
And then so with that 4 pi just be vector hours.
Right. So if we want a vector that has that magnitude, and they told us that the direction was the positive x direction. So therefore, the vector is 4 pi and 0, 0. That's the area vector for this circle with orientation in the positive x direction, because its area is the magnitude of the vector and its direction is orthogonal to the region according to what they specified. So they could have said the direction is in the negative x direction. They could have said that, and then the area vector would have been negative 4 pi, 0, 0, pointing in. So at the end of the course, we're going to see a lot more about area vectors. Does this answer it, Jake?
Yeah. I just wanted to, For some reason, so I looked in the answer to make sure I did it right.
Yeah.
And they put it with the I symbol.
It's the same thing, right? So there's two ways to say the same thing. So just 4 pi, you could just say 4 pi I and you're done.
Yeah.
Yep.
Okay.
It's the same vector, right? Just we have two different ways of expressing. And what is 4 pi I? Why are they the same? What is I?
1, 0, 0.
1, 0, 0. And if you do the math, what do you get?
4 pi.
See that? They're just two ways of saying the exact same thing. They're both ways of expressing a vector. Component form and standard unit basis form. Good on 55? Okay, additional problem A. Where's that? Is that back from the previous assignment?
Um,
Okay, so he's going to start at 0, -2. And in the end, he's going to arrive at 2, 3, like this. And he starts by walking 5, 1, which is something like this. So that's just a direction. It doesn't matter how long I drew that vector, right? I could have drawn it 1/5, 1, or sorry, 1, 1/5. I could have drawn it 25, 5. All we care about is that he starts walking in that direction. That has nothing to do with the distance that he went on that first leg, right? Where did he turn? He turned, so his turn was so that he made a right angle. So he turned right here, so that this was a right angle. So let's call our starting, so this is 0, 2, 0, -2. I'll call that P. And then let's say the turning point is Q. We don't know what that is, right? And then the final point was 2, 3. How are we looking? Do we got the problem? Do we understand the problem? We got a good picture? Yeah, so that these are, when you're doing problem solving kinds of things, don't start your thinking off by, okay, gather the information and what formula do I need to get an answer. Rather, it's about like understand the problem, understand what's going on, draw pictures, identify unknowns, identify things you know, and just really just try to know your way around the problem before like trying to apply some method, okay? It's going to be really helpful. So what do we need? So if we had that point Q, so what does it ask for? Yeah, it asks for this. Okay, so what are some things that if we knew, finding Q would be easy? So what kind of thing, if we knew it, would make knowing Q easy? So like I'm thinking backwards now, right? Thinking backwards to the problem. Which vector?
Vector QR.
He said the vector QR. If we knew the vector QR, could we find Q easily? Yeah, because we know the coordinates of R, right? If we know the coordinates of R and we know QR, then Q would be easy. So let's think about that. What is, I'll make that orange. That's vector QR. So is that anything we know in the situation? Do we have a tool to find that? What's that?
Final minus initial.
Except Q is our initial. We don't know. So we're going to use use QR to find the initial. So other ideas? What does this relate to? Yeah, Colin.
We could do vector projection
Okay, of what onto what?
from P to R,
P to R, and then that onto what?
and then that onto PQ.
Right. And how would that help us find QR? So yeah, so I could find the vector PR, and I could do the vector projection of that onto, I called it vector V, right? So it's not really PQ because we don't know what Q is, but onto V, right? This black vector down here, that's our vector V. So the projection of PR onto V. Is that the orange vector QR? Does it help us get the orange vector QR?
Wouldn't even
Well,
need it.
if we did the projection, we wouldn't need.
We'd have PQ, we could just find it with P.
Right. So yeah, so QR would be one way to do it, but look, if we do that vector projection, then it's even a quicker route because the vector projection is the green vector. And with the green vector, is it easy to find Q? Yeah, so this is just a matter of, like my hint, just a matter of using the projection vector PR onto V. It's like then you're one step away from getting Q. Okay, so again, this does not, the whole advantage to this is does not require finding any angles, right? That was the whole advantage because it is simply what? It's going to be PR dot V over
magnitude of v
magnitude of v squared
times v.
times v. No angles required. You just follow, now you just follow your nose, and this is the green vector. So PR, that one we can do final minus initial, Kyle, because we got it. So 2, 5, right? Check my math. So we got 2, 5 dot 5, 1 over, I think this is square root of 26, is that right? Squared is just 26 times vector v is, so this is 10, 15, 26. Check my math. And then I want q. So how do if I have p and the vector from p to q, how would I get q? They're saying add in the front. Does that make sense to add the coordinates of p to the components of pq, and that would give you q? Does that make sense? What are the components of q? Or sorry, the components of pq. Remember what we said components were in the first day class? Amounts of the meaning of a component of a vector. Since they're mobile, they're not x and y values, right? So this green vector, I could write it anywhere, right? Vectors are mobile, and so it would always have these components. So what do those components mean?
The direction.
So we said amounts of variation, right? So it's like the variation in the x direction and the variation in the y direction, or amount of change. So do you see how that's consistent for all these vectors? How much x changes is going to be the same for all of them, and that's the x component. So if we started with an x coordinate of 0 and added the amount of change, would that give us the new coordinate? Exactly, right? Exactly. That's perfect, right? So start with a coordinate, add the amount of change, you get the new coordinate. So that's the people that said add were right. So this is 75 26 plus 0. And then 15 26. Plus -2, or -2, yeah. And that's going to be the point Q. Questions about this one? So yes, that's it. Find the vector PR. The vector projection onto the vector V is the perfect vector. It points right at Q. Right? It takes us right to Q.
Is there an equation to find QR without doing the projection?
Okay, great. So not without finding the projection, but now that we have PR and we have PQ, how can we find QR? This is important because what we've really done, which is an important thing, is we've resolved PR into its components, the green component and the orange component, according to V. So we had PR in components according to X and Y, but now it's like you're setting a new frame of reference. Instead of X and Y, you're like angling it up V. And so what are the components of PR relative to V? Well, that's the green and the orange vector. So if I've got the green vector and I've got the original vector PR, how can I get the orange vector? Philip, do you know? So I got PR and the green one. What's the quickest route to getting QR? Yeah, someone dying to answer? Yeah. Okay, good. What were you going to say, David? Yes. Subtract what? Oh, right. So yeah. So yes, that's one way to do it. So now we've got the coordinates of R and Q. So we could just do final minus initial, or we can do it by vectors. We can do what? You guys are saying up here in front? PR minus PQ, right? Because those vectors are tail to tail. PR minus PQ would give you QR. So either way, you could do the coordinates of R minus the coordinates of Q, or you could do vector PR minus vector PQ. Both would give you the vector QR. Right, so the whole point of the vector projection, it gives you the vector component of one parallel to another, right? So that green vector, it's going to be some scalar multiple of 5, 1, because they're parallel. Good, anyone else? Any other discussion on this one? All right, so we didn't do a line problem. Is there one line problem that we can do? You're dying to see? No one requested a problem about lines? Jacob, you beat him by a hair.
Lines number 1, number 5. It's the one about creating a line function orthogonal to.
Okay, cool. Let's do that. So,
It's already got.
so did you notice in the video I pretty much do all of this number 4 component? Did you find that? Okay, good. You should have. And that was on purpose because we didn't really get to do examples in class, so I just wanted you to try these as best you could, and then definitely look at the video here, starting at, where was it? Starting at 3630, and I just start doing all these problems, okay? So let's look at number 5. Maybe that didn't make the video. Didn't 5 not make the video? Okay, sure. I don't want to do that. Let's see if I can make this bigger here. Okay, cool. So the equation line through the point and orthogonal to L2. Okay, so let's draw a picture. Remember, understand the situation, draw a picture. So here's L2. And L2 was given above, right? Can someone read that to me? Was it given parametrically?
Is it from number 4?
Yeah, from the previous problem.
So it's 1, 3, 4. And then, oh wait,
Yeah, that's fine.
sorry. And plus 4s minus 2s plus 5s.
Do I have it right?
Yeah.
Cool. And then we got 0.11. 111. So what are we looking for? This line. So we'll just call it L3. And so what do we know about our given line? There's some point on there, right? What point do we know for sure? That's the easiest one, right? Can you find other points easily? What would you do to find other points easily on this line? How does this generate points? You just pick any S you want. So you just pick different S's, right? So I think you're talking about 4, negative 2, 5, the direction, right? And so that multiplying it by anything you want is picking values of S. Yeah, so picking values of S magnifies, scales the 4, negative 2, 5 direction vector, and then generates points on the line. So, and then what's the direction of this line? So we got the point, 1, 3, 4, and then, yeah.
It's 4, negative 2, 5.
4, negative 2, 5. Right, so from the parametric equations, this is our parallel vector to the line. That's our direction vector. This is our known point, 1, 3, 4. And we could easily find lots of other points by picking values of S, cranking out order triples x, y, z, right? So how are we going to do this? So look, I've got this point up here. I got this vector 4, -2, 5. I got this point 1, 3, 4. And I'm trying, what am I trying to do? I'm trying to get, all I need to write the equation of L3 is what? What's the thing I need to do? Direction vector, right? I need a vector parallel to, perpendicular, or parallel to our line, right? So in the direction of our line. How can I do that? How can I get a vector that's perpendicular to the given line? Tell me your name one more time.
Right.
Ryan.
Make a vector projection of the vector from 1, 1, 1 to 1, 3, 4 onto the line, or onto the,
So make this vector, and then do that vector projection onto what vector?
4, 2, 5.
Right, if I project this vector onto this direction vector, do you see which vector I'll get? Whoa. So it's basically, so the length of this vector, the one you're projecting on, doesn't matter, right? The length of the vector you're projecting on doesn't matter. So it's basically projecting this vector onto this given line. So do you see that that projection will be this vector? Okay. And then, so Ryan, how do you see that that helps?
You're able to, sorry, the words are.
No problem, take your time. So you're saying the projection of, let's call this A.
Cross product of those two, correct?
Cross product will be orthogonal to the screen. So if I do the projection of A onto B, it is helpful. How can that help us get, what do we really need? We need
Sine. Yeah, subtract B from the point on the line, or vice versa.
Yeah, I shouldn't have said B here. The projection of A onto, I'll call this vector C. If I do the projection of A onto C, which is what I'm calling the direction of the original line, I'll get this vector B. And then to get vector V, I can do A minus B. That's one way to do this. There may be others. Did anyone have a different way that that worked? Yeah, Lucas.
I just worked around the dot product and just did some algebra to find an orthogonal vector, and then I just
So kind of trial and error?
kinda. So can I do it on the board real quick?
Yeah, sure. You can do that on the board while I'll finish out this one.
Okay.
So projection of A onto C is, what is that? A dot C over C squared. So A is 0, -2, -3. So A dot C is 0, 4, -15, or 0 plus 4 plus -15 over C squared, or the magnitude of C, so that's 16, 20, is that 45? Check my math. Okay, this is pretty ugly, but let's see here. Yikes, -11 45ths. So -44 45ths. I think I'm going to like Lucas's way better. 22 45ths. And -55 45ths. That's what? That's vector B. And then we want A minus B will be vector V. I'll do it in red. So vector V is A minus B, or 0. So positive 44 55ths. 45ths. 2 minus that. So that's negative 90, negative 112. And negative 35, 190.
Yeah.
Now, all we need is direction, right? So all we need for V to write this equation, this line, is any vector parallel to V. So we can get rid of these now, right? Does that make sense? So if I'm writing the equation of the line, any vector parallel to the line is good to write the equation. So since they all have 45 in the denominator, I can just multiply by 45, and that's a valid direction vector for the line. Does it make sense? Any vector parallel to the line is valid for writing the equation of the line. So then I'd have, my point is 1, 1, 1, so I'd have 1, 1, 1 plus t times 44, negative 112, 90. And I could divide this by 2. I could find, looks like I have a factor of 2 in all of them. I could divide that by 2 if I wanted, but don't need to. So let's see if our lines are the same. Lucas, did you get a line actually? 1, 1. We are not parallel, so something's up. So if you have 1 and 1, then I have to have the same numbers here.
Okay.
So either we're off or you're off. I'm not sure.
So what I did is I just set up a dot product type of thing and solved it kind of algebraically. And I put it to 0, then laid it out to this. So I put A as 1 and B as 1. So there's your A and there's your B for your vector. And then after that, I solved, which you get 2 plus 5c, and then you okay. And then you subtract 2, and then you get c equals negative 2 over 5 for your vector, and then you have your dot, and then you have your t times that.
Okay, so one of us is not right. Does anybody know? I know, so I know what happened. Does anybody know what's going on here? Yeah, Max.
Well, here's the method, it's like, it's actually, I did that too, but, like, I think the issue is, like, when we try to dot the original vector to make it equal to 0, the second vector could be pretty much any other vector than we have. Like, I had, for the vector I came up with was 1, 2, 0, which is, like, different than yours, so, like, any vector we could make is gonna have, like, widely different, like, magnitude, like, different direction, all that, and that second vector we do make, it could not even be like couldn't even be on there's a chance it could not be on the same line as 1, 1, 1, maybe orthogonal as well too. So.
Do you understand what he's saying? So here's a vector in space.
Okay.
Is there just one direction of a vector that's orthogonal to that vector? Are there more than one? How many are there? Yeah, any vector parallel to that plane right there is going to be orthogonal to this vector. So so you imagine like a clock. Any vector in that plane is going to be orthogonal, but will not be a direction vector for this particular line.
Okay.
Does that make sense?
So
we got to get so you found a vector that was orthogonal to this one, but because we're dealing with three-dimensional space, it's not parallel to the line that we're drawing. Does that make sense? Because you could have all these vectors. You found one of these, but not necessarily the one
that's
parallel to our line.
To the
Yeah.
imaginary vector that you
Yeah.
found.
But it's a great idea, right? So like all your thinking is correct, but you just forgot about three-dimensional space, right? You just forgot that there's an extra degree of freedom there that you didn't take into account. Okay, does that make sense? And then, so does what we talked about there make sense, and then does this solution make sense?
Is there a way to make that way work, or no?
You'd have to bring into somehow you'd have to bring into account the other information that you know, like because basically he's found some vector perpendicular to 4, negative 2, 5, so it could be any of these vectors. So we need this one, right? Not this one or this one or this one or this one, but this one. So that's where the 1, 1, 1 comes in. So yeah, you need it. Yeah, I think this is I have to think about it more, but whatever he'd have to do to embellish that would not be any easier than this. Does that make sense? It wouldn't make it any easier. All right, last chance for questions on the homework.
I suggested B. That's all. I thought we were doing problems on board today, so if anybody else wants B, the additional question B.
So it's actually a lot like the last two we did. It's a lot like the Gandalf problem and this problem. You use just look for vector projection again. So for time's sake, I think we'll move on. That's okay. So, but I think with having done those two last examples, I think you can piece it together from those two. All right, so let's press on. So did you see my announcement? I think to have a new homework assignment and give you a review for the test over one class period, I think that's rushing, right? So because what we're going to do today is on the exam. So I'd rather have a homework on this stuff and then give you the weekend to do like some review and study, and then we'll do the exam Tuesday, okay? This is better, I think.
Do you give out review problems?
Yeah, I have a whole sheet of review. But it's not, the test is not just the review problems with different numbers. You got to go back and study the lectures and the homework, okay? So it's just extra practice. It's not a reflection of it, like what the test will be like, okay? Okay, so we talked about lines, now we want to talk about planes. So planes are a different animal than lines because, so what do we say? We could generate all the points in the line. Just by changing the parameter, right? So we know this is our equation of a line. Know it well. And how do we generate points? How do we generate different points on the line? By doing what? Okay, so those are, yes, those are right. So what, in this equation, what is it that generates points on the line? Changing t, right? So you have this given point, and you have this given direction, and so t is a variable, right? So by letting t vary, every time t varies, you get a new xyz, and that's a point on the line, right? And so that generates points on the line. So a plane is a different animal, right? Because the fact that you only have one thing that you have to change, one value you have to change to generate points, it's like, because it's a one-dimensional object. The line is one-dimensional, right? Plane, different animal, two-dimensional. Okay, so it's going to be different than this, right? Our equation of a plane is going to have like going to be like apples and oranges to a line. So we're going to develop that in a second. Now, what is the same about a plane and a line is that to write the equation of a plane, just like a line, we're going to need a point. And an orientation, right? So what was the orientation of the line called? What did we say it was the orientation of a line? Direction vector, right? This thing right here, this guy right here. That was our direction vector for the line. So, point is easy. It's a point in the plane, right? So we've seen that before. So that's just pretty straightforward. So what about the orientation of a plane? What about a vector that's parallel to or in the plane? A vector that's parallel to or in the plane. Does that uniquely determine the orientation of the plane in space, meaning like kind of how it's positioned or angled in space. So some people are shaking their head. So tell me your name again. You came late to the class? No, in the black shirt. Yeah. Was it? Sebastian. You're shaking your head. Why not? Why doesn't that blue vector uniquely determine how this plane is angled?
Well, because it's just one vector on the plane. If there's other vectors on the plane that can determine where it's going.
Okay, cool. That's another way to think of it. So there are other vectors that are parallel. So why don't those determine the plane? What about looking at the other way? If I give you a vector, is there one unique plane that's parallel to it? If I give you a vector in the plane, I give you a vector, is there only one orientation of a plane that's parallel to that vector? Yeah, because if you think of that vector that you start with as an axis, you have all these different planes that could rotate around that axis, and then all those planes are parallel to that. Does that make sense? So this isn't going to do it. A vector that's parallel to the plane isn't going to lock in an angle or an orientation of the plane in space. Because given a vector that's parallel, you have an infinite number of planes that could. So how are we gonna? What kind of thing is going to lock in a direction of a plane in space?
Another vector.
What's that?
Another vector.
Yeah, another vector. So if it's not parallel to the plane, what kind of vector is going to, will a perpendicular vector do it? So if I have a vector like this, is there only one orientation of a plane that's orthogonal to that?
Circle.
No longer stick, but there's a stick. Good. Pointer, excellent. All right, so here's my vector. Here's my vector, okay? Like this. So once I set that vector, so is this plane orthogonal to that vector?
Yeah.
Okay, so do I have any wiggle room? Can I change this and still have it be orthogonal? Okay, so I can move it like this, but is that a different orientation or the same orientation of the plane? Same, just different location, right? So the only thing if I'm orthogonal to that vector, the only freedom I have is the location of the plane, but I have no wiggle room. It's locked in terms of its orientation. Does that make sense? So that's what we want. So the orientation vector is going to be an orthogonal vector. Now, why is that confusing compared to a line? Why do you have to file this away in your brain, right? What was the orientation of the line? The vector was parallel to the line. Orientation for a plane, the vector is orthogonal to the plane. Does it make sense? So you got to file that in your brain because we're gonna use ABC for both. So when we're talking about a line, this ABC vector is parallel to the line. Okay, so this is what we want. This vector is going to lock in how the plane is oriented in space. I have no wiggle room with that. No wiggle room to change its angle to the axes or to the planes, the coordinate planes. All right, so what am I going to do? We're going to, so that is my, so the orthogonal vector is any vector orthogonal. So like I said, we're going to call that ABC. What does this vector represent? So position vector that gives me my point in the plane. So this is it's like my x naught, y naught, z naught, my given point, which could be any given point in the plane. Okay, and then, so this red vector then, like the red vector I had before for the line, is going to be every point in the plane. So this is going to be every point in the plane. So that's represented by x, y, z, right? Variable point. So x, y, z is every point in the plane.
Oh, you mean like that red one can move to any?
Yes, and let me, like this. Okay, every point in the plane. Okay? So we need a relationship between these three vectors. We know that what? We know ABC is orthogonal to the plane. XYZ is any point in the plane, and X0, Y0, Z0 is some fixed point in the plane. So what vector relationship can we write between these three? Any ideas?
X naught, Y naught, Z naught, cross product.
If you did a vector from XYZ to ABC, and found the projection, that would just get you to the X0, Y0, Z0. Not sure how
Okay, good idea. So what do we know? So ABC is orthogonal to what? The plane. So what would ABC be orthogonal to?
The vector between
Lucas.
Y naught. So it would be the vector that the points lie on, right?
Right. So it'd be orthogonal to every vector parallel to the plane. So we can write a vector parallel to the plane, which would be this one. That's in the plane, right? Or parallel to the plane. So how do I write that mathematically? What vector is that? These are tail to tail, right? Completing the triangle, it'd be what minus what?
X minus X naught.
Yep. Yeah, it's this red vector minus the black vector. And now what do we know about these two vectors? Perpendicular. So that's the key to writing the equation. What can we, if they're perpendicular, what mathematical statement can I write? Dot product is 0. So I can do A, B, C, dot, that whole thing, exactly, equals. So that forms the equation of the plane, right? Because as this point moves around, this is all points, right? The red one's all points. As that moves around, then that black vector that I drew will always be parallel to the plane, right? Because it'll always be from a point in the plane to my given point in the plane. So I'll always get a vector parallel to that plane, which will always be orthogonal to ABC. Okay, so now here we do the math. And when we do the math, all the vectors go away. Are you with me?
Yeah.
You follow that?
You should drop that.
So I just did the dot product, right? You multiply like components and add. Yes, please.
So the dot product shows us the vectors that can then, I guess, are parallel and perpendicular to the plane then?
Those two vectors are perpendicular. The vector this vector is always in the plane, or parallel to the plane, and this is always orthogonal to the plane. So those are always orthogonal. So the dot product is 0. Okay, and so then this is one form of the equation of a plane right there.
Usually like that.
Well, so this is how you start if they're telling you to write the equation of a plane. So in order to write the equation of a plane, what two things do you need? Every time they say, find the plane such that blah, 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 write the plane such that, then you should think, oh, I need two things. What do I need? I need a point, some point, x0, y0, z0, and an orthogonal vector, right? Orthogonal vector, which is ABC, orthogonal to the plane. If I have those two things, plug and go, right?
And then in your equation, just X, Y, and Z are just gonna be left alone. They're gonna be there.
Right, because what are those? What are
It's just
x, y, and z?
whatever point you choose to put in. Okay. Right?
What do they
On that
represent
plane,
then?
Every point on that plane.
Every point on the
Yeah.
plane, right? Every point on the plane, that's right.
Mhm.
So they stay variable, right? They stay x, y, and z because every order triple x, y, and z that makes it true is a point on the plane. Okay, now I can take that and I can do some more math, right? I can distribute and change it around. You do ax plus by plus cz equals, and move all these others to the other side. So there's just algebra. Nothing scary here. I just did 2 steps at once. Is that okay? I multiply it out and move those 3 terms over. Now this was all stuff that we knew, right? Those are all values. A, B, C, x naught, y naught, z naught were all numbers that we started with. So that's just a number when you do all that. So it's just called D. So here's another way to express a plane. And this is what you'll often see when you're given a plane. They'll say, a given plane, the equation of a plane is such and such. So when you're given a plane like that, what would you know right away? What could you pick off easily and quickly about the plane? Jacob says the orthogonal vector. Agree with that? Yeah, that'd be the coefficients, right? You take the coefficients of x, y, and z. You would immediately know from those coefficients what your orthogonal vector is. What about points on the plane? So let's try one. Here's an example. 2x minus y plus 4z equals 6. So what do you know right away?
The orthogonal vector is 2, -1, 4.
Good. 2, -1, 4 is orthogonal to that plane. And then how can you get a point or points on the plane? How could we know what point or points on the plane are? So what's the idea behind it, right? If I have a point that's on the plane, how does it relate to this equation? If I have an ordered triple on, what would be true? So for instance, is 5, -1, 3 a point on this plane? Is 5, -1, 3 on the plane or not?
Do you have to check if it's perpendicular to that?
Okay, he says you have to plug it in, and if it equals 6, it's on the plane. What do you think? So 10 plus 2 plus 12. So this would be 10, right? 10 minus, or sorry, plus 1. 10 plus 1 plus 12. Do I do the math right? Is 23. Equals 6? No. On the plane? What would have to be true for it to be on the plane? Right. Ordered triples that make that equation true are points on the plane. Ordered triples that don't make the equation true are not on the plane. It's really nice, right? What a great thing. So it's the mathematical equivalent of the plane. It's not just a label for one of the planes in space. It's not just, here's the name of this plane, right? It's mathematically equivalent because it's telling you all the points that are on the plane by the points that make that equation true. And the points that don't make the equation true are off the plane. So see if you can find 3 points on the plane. Can you find 3 points on the plane? Anything you want, right? Anything you want. Any ordered triple that makes that true will be on the plane. So make it easier on yourself.
Make 2 of them a certain number and solve the last one.
0, -1.
So now I made x and y y0, and just solve for z.
So 1
4 or 6 over 4. 1.5, right? But just 4z equals 6. Z equals 6 over 4, yeah.
And
And then
Okay, Raj, did you find one?
Why is not 0?
063? He wants 063. Okay, the rest of you, verify that that's on the plane. He says 063. So verify. Is it on the plane? Okay, they're saying yes. Let's see. Tell me your name again, sir.
Brandon?
Brandon. Did you find one?
Yeah. You want,
Yeah.
101.
101. He's on the plank. Do we push him off or is he okay? Walk back to the ship. Okay, Chris, did you get one?
yeah, I got 2, -2, 0.
On the plank. 2, -2, 0. Push him off or is he on the stay on? Is it good? Tell me your name again. Tyler? 0, -6, 0. So picking 2 coordinates to be 0 are the easiest ones. And then what are special about those points? The points where you pick 2 to be 0, what can you say about those points? Right, that's where the plane, where an axis intersects. This is telling us that which axis intersects the plane where? Y-axis intersects the plane at y equals -6 to the left, right? -6. So where does it cross the other 2 axes? Some of you found that? What's that?
3, 0, 0.
So tell me about crossing an axis then. What does that mean? Right, good. So it crosses the x-axis at 3, z-axis at 3 halves, right? So it's going to cross the z-axis at 3 halves. So that, knowing the 3 axes crossing points is a way to make a quick sketch of the plane. If you want to sketch it quickly, because what we know, 0, 0, -6 now, 0, 0, 3, and 3 halves. So you can just then draw this little triangle here, and it gives you an idea of what this plane is oriented in space. See that? So yeah, if you want to. Yes, please.
Is there any way, what website is this that you have with all the vectors and planes? Like,
Oh,
is
it's
there-
not.
is there-
It's software. It's
Oh, it's a software.
it's a graphing software. It's a lot like Desmos. That's free.
Oh.
You heard of Desmos? Yeah. So it's this is a little more sophisticated. It does a little bit more than Desmos, but if you can get Desmos for free and it can do all this stuff.
Okay.
Yeah, sure. Yes, sir.
Just as a note, there's an app called GeoGebra. That's basically it's GEOG.
Yeah, you can draw planes and things in space.
Yeah.
It's a lot different than this.
Yeah, but it's just for the visual.
For visually, absolutely, absolutely, yeah. Max?
What's the D, like, 6, what does that represent again?
Yeah, and then we didn't talk about that. So it's whatever ax naught plus by naught plus cz naught. So one thing you can think about is like for this. So if I was to change that number, how would the plane change and how would it not change? So what would change about the plane and what wouldn't change? So if I made that a 12 or a -2, or so how would the plane change? Elena. So okay, so I should have said this at the beginning. So a plane runs infinitely in all directions, right? So this is just one little trapezoid from the plane, which wherever the edges are, it's going to keep running forever. It's just, if I did that, then the whole screen would be yellow and you wouldn't see anything, right? So yeah, so planes run infinitely in all directions. So it wouldn't make it bigger.
Does it change where it like touches all the axes?
Okay, so it changed where it touches the axes. So, but what does not change if I change that number?
Yeah.
Does the orthogonal vector stay the same?
Yeah.
Yeah, because the orthogonal vector is these coefficients. So if I keep the orthogonal vector the same and then change that number,
You're just moving it out.
moving it, right? Without tweaking it, right? It's not going to, what's the word? It's not going to change its orientation. It's just going to move it. So basically, that vector, if this plane looks something like, does it look something like this, maybe?
Yeah.
Changing that D value, 6, would just change it like this, and the orientation would stay the same. Does that make sense?
And ABC is still perpendicular.
Yep, so for all, it's all, making that a variable gives you all planes that have that orientation, which would be all parallel planes like that. Good discussion. Ready to try some practice problems? Oh, no, one more question, Tyler.
Just a question. How did you determine what the direction vector of the red line would be? Did you just know that would be a vector of any x, y, z?
Yeah, so this is any vector from the origin to a point in the plane. It's every single, so it's representing every point in the plane. So I can move it around a little bit to give you the idea. So it's representing just every point in the plane. So I can move that around, and it'll. So no matter where that point is, then the vector from x naught, y naught, z naught to that point will be parallel to the plane, and therefore orthogonal to my orthogonal vector, and this will always be true. Okay, practice. Here we go. You guys can work in groups on these problems for a little while. So as much as you can, try to think of this as practice. Listen, practice in the ideas, in the visualization, right? As much or more than like how to solve and get the answers. So try to really be thinking about like drawing pictures, visualizing what's going on as a way to help you solve it. So these get progressively harder. It starts out pretty easy. And then each problem gets a little progressively harder. It requires more thought, more good pictures, more discussion, but they get progressively harder. Okay, so let's see how we do. I need a drink of water. Oh, sorry, I didn't first say that. Normal, perpendicular, and orthogonal are for us, and R2 and R3 are synonymous. So normal, forgot that. Orthogonal, perpendicular, equivalent. So often we'll call this vector for the plane the normal vector. The orientation vector for the plane, often it'll be called the normal vector. That means it's orthogonal or perpendicular to the plane. So pictures. Here we go. You don't have to draw exactly these perfect lines in R3. You can just do a generic kind of situation. So you just draw two lines, okay, and then you consider like the plane that they're in, something like this, a parallelogram, okay, and so we need to write, this is going to be plane P2. We need to write the equation of this plane, and so if we need to write the equation of the plane, we need two things. What do we need? What's that? Giorgio. Orthogonal vector. Normal is easier to write, a little shorter. Normal vector, orthogonal vector, yep. And a point on the plane. Are any of those immediately apparent? Easy? How do we have a point on this plane?
1, 3, 4, 5.
Yep, so here's one possible point. Any point on this line, any point on this line. How could we get other points? Plug in other S values, right? Plug in other S values here, plug in other S values here, but you don't even have to do that. You've already got 1, 3, 4 or 5, 1, is that 9? Take your pick. So we'll do 5, 1, 9. Doesn't matter. So we're halfway there. All we need now is what? harder. It's not hard, it's just harder. Okay? How are we gonna, we got these two lines, and I need a vector that's orthogonal to both those lines. Lucas,
Wouldn't you just take the cross product of the two vectors here?
he wants the cross product. So when you say the two vectors, which two vectors?
So 4, -2, 5.
Okay.
And -1, -3, 2.
So 4 to -5 relates how to the first line? Parallel? In the same direction as that line, and then? -1, 3, -2? So look, I've got two vectors in my plane. I need a vector, what? If it's orthogonal to the plane, it's orthogonal to both those vectors. And then you remember? Cross product. That's exactly what the cross product does, right? Cross product, given two vectors, it gives you a vector that's orthogonal to both. Can you finish it? See if you can you finish the problem? See if you can finish it now. So you got, what, -4, -2, 5?
It's a positive 4.
Thank you. +4, -2, 5. And -1, -3, 2. I've got my point. I'm trying to find my orthogonal vector. Okay, there's another kind of easier one up for grabs if someone wants to do it on the board, number 6. If you're good on number 3 and you want to, we could have someone else put 6 up for 6 is more belongs more around number 1 or number 2. You can do it. I should say and parallel to the plane. Kyle, you okay?
I'm fine.
All right, how did number 3 go? Anyone have a question on number 3? Can you finish it off? Okay, so what do we need to write the equation of a plane? Yep. Do you see where I got the point?
Yeah.
That's from the second line. I just pulled off the known point from the second line. So all I have left to get is the orthogonal vector. And I have two lines that are in that plane. That means I have two parallel vectors to those lines. I drew those in red. So the vector that's orthogonal to the plane will be orthogonal to both of those red vectors. Does that make sense? So that's a concept from last week. If you have two vectors and you want a vector orthogonal to both of them, we learned a tool that does exactly that, cross product. Okay, so far we've seen two different instances of equations that contained x, y, and z. Do you remember what those are so far in this class? We were talking about a topic, and to represent this physical thing, it was an equation of x, y, and z. We've seen that twice. So actually, lines is a vector equation. So it's not really one equation that has x, y, and z in it, because it was like 3 equations, right?
Oh,
So planes, and what was the other equation we've seen? It was just briefly, like the first day, second day. Spheres, remember spheres? Remember what the equation of the sphere was? Who remembers the equation of a sphere?
it's like 4/3
Like 4/3 R squared, 4/3 pi cubed.
No, that's the volume, right? So we want an equation that represents all points on the sphere. X minus plus.
Y minus b squared and then z minus c squared.
And do you remember where this came from? Equals?
Equals r squared.
Remember where that came from?
2 vectors and
Remember, it was all points the same distance away from a given point.
Oh, so it's in there.
So right, this came from like the magnitude of a vector from the radius from the center to the sphere. Remember that? Okay. And what was our equation of a plane? That was our other one.
A is supposed to be y. C is going to be dy. Let's see.
So these have so an equation of a line is not like this, right? It's either that vector equation or the 3 parametric equations. So that's like a line is like apples and oranges. But there's something similar about a sphere and a plane. They both have something in common that results in the fact that their equations are a single equation with x, y, and z in them. So what's similar about a plane and a sphere? They're both what? Sphere and a plane are both examples of what kind of thing? So equations of x, y, and z express all ordered triples that form a, starts with S. Chris got it, surface. Surface in space. Those are surfaces. So they're flat. They're flat. They have they're two-dimensional and they have no thickness, right? That's what a surface is. It could be curved, like a sphere. But spheres and planes are both examples of surfaces. And so the equation of a surface is always a single equation that has x, y, and z in it. Well, so one of those could be missing, like z could be missing. It's still a surface in space. But generically, if it's a single equation with x, y, and z, it will represent a surface, like a sphere or a plane. Okay, so ellipsoids are stretched spheres. So we'll just finish with ellipsoids. So what you have is you start with a sphere, and if you divide by r squared, you get this. Do you see that? So now if you have a radius that corresponds to x and y and z, if you let those be different, right now it's the same radius for all of them. I divided by r squared, right? Now if I allow those to be different radii in the different x, y, and z direction, it's like I'm taking the sphere and I'm stretching it or smushing it in those directions. Does it make sense? So what kind of thing do you get? You get like a rugby ball, or like a UFO, or a pill, like if you or a pillow, okay, like a oval-shaped pillow. So if you allow a different radii in each axis, then rather than the same radius r squared for sphere, you could have like an x radius and a y radius and a z radius. Hello, what's going on? Where are you? So that's called an ellipsoid. An ellipsoid is based on, like a sphere is based on circles in every direction. An ellipsoid is based on ellipses. Or it could be circle, but if you allow for ellipses in the different directions, then you get what's called an ellipsoid. So let's just figure out what this ellipsoid is like, and we'll be done, okay? So I want to get this equation to look like this one. So it's going to be, no, it's not that hard. Good. So if I'm multiplying by 4, that's the same as dividing by what squared? Isn't that dividing by 1/2 squared? And then if I'm dividing by 9, that's what squared? And now I just got nothing, so I'm dividing by. So this gives us, this form now gives us ellipsoid, and gives me my 3 different radii in the x, y, and z directions. So sketching that. Oh, so and then what about the center? So just like the center of a circle, what would be the center of this ellipsoid? or sphere, right? Just like the center of the sphere was A, B, C. What's the center of my ellipsoid? 3, 0, 2. Okay, so I'm going to come out 3 like this in the x direction. Go up 2. There's my center. And now in the x direction, my radius is. So I'm just going to go a little bit forward, just forward a little bit, front and back. I'll do my best to make a good picture here, but it's going to get a little messy here. And then the y direction, it's stretched times 3, right? Stretched out by 3. So I'm going to go 1, 2, over 3, and over 3 this way. And then in the z direction, just 1. So up 1, down 1. So those are 6 points on the, can you imagine it before I draw it? I'll do my best to draw it well. Here we go. So this is parallel to the xy plane. I got this ellipse here. So that's the ellipse parallel to the xy plane. And then I've got one parallel to the, okay, it's not so bad so far. Last one, last ellipse, looks like this. So centered at 302, and then x-axis radius 1/2, y-axis 3, z-axis 1. So we got a moved and squished sphere, which is an ellipsoid.